Get started. First things first. As you know, we're finishing up section 3.4. We're going to do 3.4b today, which is on the critical values and the first derivative test. And from that, we've got one more section which I'll cover on Friday, which is section 3.5, absolute max, absolute min stuff, which means we're about to have our next test. Which means you can anticipate from me on Friday, probably try to get it out and actually post it onto your Canvas site, your next homework set, the traditional homework set that I'm going to try to mimic what your test is going to look like. Now, if you're honest with yourself and you look at the last test and you look at the homework set that I gave just before the test, you should see a huge pattern here. That homework set, the traditional homework set that I give you guys, does look just like, very similar to what the test is going to look like. So that's the way you need to study, because I'm trying to make sure that you guys understand the questions and stuff. That this is the style of question and the word problems and the wording that I'm going to use on your test to make sure that when you're taking the test, you go, I know how to do this problem, and you just knock yourself out and stuff like that. So. Before we get started in terms of today's lecture, there was a couple of questions that folks have had for me on the Hawk system and stuff like that. And this is one of them. This was on your certify. But one of the other questions, before I get to this problem, was that this. When you go to the Hawk system, a lot of people are complaining about, well, when I actually type in the question, because you said, Dr. Taylor, I didn't have to clean this stuff up, and I repeat that. You do not have to clean up your derivatives, even on the Hawk system. You basically just do the problem. But you got to be careful. You put a parenthesis in the wrong spot, you don't put parentheses around the numerator, parentheses around the denominator, you're going to get it, quote unquote, wrong because you got some kind of typo on it. So I was going to show you guys that what I mean by you don't have to clean this thing up. For example, here we're on the Hawks. This is on our practice session here, but it's the same idea on your certified. Look at this problem here. Y is equal to the fourth root of 7x cubed plus 6. Well, one, I don't do fourth roots. Fourth roots is also known as a 1/4 power. So to take rid of this guy, what I see is 7x cubed plus 6 on the inside and that 1/4 power on the outside. That's a chain rule. Chain rule. Derivative the outside, inside stays the same, time derivative the inside. So, derivative the outside. I'm going to bring down that 1/4. I'm going to parenthesis. And I can do a 1/4, 1 divided by 4. And automatically, Hawks, even though I didn't push the keypad, we'll put this thing in there. It's 1/4 here. And I can get rid of this part over here. 1/4 times a parenthesis. And inside the parentheses, the inside stays the same. 7x cubed over arrow, 7x cubed plus 6. And all this is being raised to the what power? You got to subtract 1. Negative 3/4. So I'm going to put a fraction in there, and it's going to be negative 3 divided by 4. Then you got to go over arrow there times, notice how I'm using parentheses for each part here, times the derivative of the inside. What's the derivative of 7x cubed plus 6? 21x squared. And I didn't clean this up. I didn't know a fourth of 21 or anything like that. I didn't submit my answer, and boom, there it is. Way to go, John. There you go. Does that make sense? You don't have to clean this up. But this also means that you're going to be very adamant about when you do particular problems that you have got to type it in exactly right. Now, I'm not going to say this thing's not a pain in the butt. It is, because typing it in, because this is a computer, I don't care what system you use, typing in a large derivative. Here's one more. We'll do this one right here. I got negative 5x to the negative 3 plus 5x plus 7 times 5x to the fourth minus 9x plus 9 squared. First rule, stop, pause, hesitate, and ask yourself, what rule am I going to use to take derivative of this thing? What's the big picture? This is a product. Yeah, I see a little chain at the end there, but the big picture is that big old times in the middle. So if you read this problem out, negative 5x to the negative 3 plus 5x plus 7 times 5x to the fourth minus 9x plus 9 squared. That times in the middle tells me this is a product rule. Product rule. Derivative the first time the second plus the first time derivative the second. So I'm going to put parentheses. What's derivative of the first guy? What's derivative of negative 5x to the negative 3? That's what going to be 15 x to the, subtract 1 makes it -4, right? And then over arrow, derivative of 5x is plus 5. You with me? That's the derivative of the first guy. Then I got to do times the second. So all I got to do is recopy the second guy, which is 5x to the fourth minus 9x. Oh, must have hit the wrong button there. Hold on. Oh, I forgot to hit the out of the thing here. That happens to me all the time. So we go back, over arrow. There we go. Let's see here. 5x to the fourth minus 9x plus 9. Get that guy out of the way. And then I'm going to raise him to the second power. Now, it's the derivative of the first times the second plus, parentheses, the first, just recopy it, -5x to the -3 over arrow. Don't forget to do that so you get your next term. Plus 5x plus 7, right? Derivative of the first times the second plus the first. Now here we go, times the derivative of the second. To take derivative of the second guy, I got to use the chain rule. Derivative of the outside, the 2 pops out front, so it'll be put times 2, right? The inside stays the same, which is 5x to the fourth minus 9x plus 9, okay? Raised to the first power, but raised to the first power is himself, right? Times the derivative of the inside. So I'm going to put another parenthesis there. The derivative of the inside is what? What's the derivative of 5x to the fourth? 20x cubed over arrow there, minus 9. And there it is. Does that make sense? And just look at it. Let's slide this thing over because this is large. It's the derivative of the first guy times the second plus the first times, and there it is, the derivative of the second guy. Chain rule. Derivative outside, inside stayed the same times the derivative of the inside. And then I submit, and you don't have to clean it up, that's my point. But you got to be very adamant about putting these parentheses in a spot. You put one parenthesis in the wrong spot, you put a plus instead of a minus, or whatever the case may be, boom, it's going to be wrong. And it's legitimate, it is wrong. So just be careful on that. But the one other one I wanted to talk about was I had students send me a question on one, and here it is right here. So this is part of your certify on section 3.2, which is still open. I opened it a little extra on section 3.2 just to give you guys some time, and I also gave you a one extra attempt on it because of these darn parentheses and the way you got to type this stuff in. So let's take a look at this guy here. It says this. This is one of your problems here. The demand function for a particular product is given by d of x is equal to the square root of negative 2x squared minus 6x plus $190, where x is the number of units sold. What is the marginal revenue when 5 items are sold? Round your answers to decimal places. All right. So here's the deal. We were looking for marginal revenue. But before you get marginal revenue, marginal meaning derivative, you got to find revenue. What is my revenue equation? Revenue is equal to what? What is my formula? X times price, or X times demand. And that price is the same thing as demand, right? Your d of x. So this would be x times the square root of negative 2x squared minus 6x plus 190. But I don't do square roots. Square roots is I have a power, right? So all I did was multiply the equation they gave me times x to get the revenue equation. Now they want the marginal revenue, which means I'm going to take derivative of this dude. Okay? But what rule do I have to use to take derivative of this guy? It is x times negative 2x squared minus 6x plus 190 to the half power. With that times in the middle, it's a product rule. Yeah, I see some chain rule action here too. Yeah, granted, it's a combo rule here, but the big picture is a product. Derivative of the first times the second plus the first times derivative of the second. Derivative of the first guy. Derivative of x is 1 times the second, negative 2x squared minus 6x plus 190 raised to the 1/2 power. Derivative of the first times the second plus the first x times derivative of the second. Take derivative of the second function here, I got to use the chain rule. Derivative outside, the 1/2 pops out front, the inside, negative 2x squared minus 6x plus 190 stays the same. Raised to the, subtract 1, negative 1/2, times the derivative of the inside. Derivative of negative 2x squared is negative 4x minus derivative of 6x is 6, minus 6. Derivative of 190 is 0. So there is my derivative. You with me? But what was the thing they asked me about this question? They want to know what the marginal revenue is if we sell, how many? 5 units. We're supposed to find R prime of 5. So guess what I'm going to do at this point? Plug in 5. 1 times anybody is anybody. So it'll be negative 2 times 5 squared minus 6 times 5 plus 190 raised to the 1/2 power plus x is 5 times 1/2 times negative 2 times 5 squared minus 6 times 5 plus 190 times negative 4 times 5 minus 6. To the negative 1/2 power. Right, thank you. All right, so now all I did was actually just plug in my 5. Now you'll notice on this particular problem, just to save you some pain and headache here, I'm going to go ahead and crunch inside these parentheses first. So I'm going to do this in parts here. So this is negative 2 times 5 squared minus 6 times 5 plus 190. And I get 110, right? So this part, this is 110 raised to the 1/2 power plus 5 times 1/2 is 5 halves. But notice inside this parentheses is the exact same thing, that negative 5x squared minus 6 times 5 plus 190, which we just calculated. That's 110 raised to the negative 1/2 power, right? And then I got to do times this part here. Negative 4 times 5, slide over, you guys can see this. Negative 4 times 5 is what? Negative 20 minus 6 is negative 26. So that's what I'm going to stick on my calculator now. So parentheses, 110 raised to the 1/2 power plus, parentheses around fractions, 5 halves times 110 raised to the negative 1/2 power over, and then that times negative 26. So I literally just, PC parted it a little bit just to get me some nicer numbers. And then what do I get? I get 4.29058165 and this would be marginal dollars per unit, because revenue is measured in dollars and X is represented by units, so it's dollars per unit. But one last thing to get the problem right here is if you go back and read the question, this font -2 thing here, we're supposed to write this answer to 2 decimal places, right? So 2 decimal places would be 4.29. So the answer that would go here would be 4.29. Does that make sense? And don't, obviously on computers don't type in units. On my test do, but no. Okay. Does that make sense? Did I lose you guys anywhere? All right, so if you haven't certified in 3.2 yet, please do so on that chain rule stuff, but there's still, notice, we're still doing problems of business. Profit, revenue, cost. Revenue equals X times price, X times demand. Profits, revenue minus cost, so forth and so on. Okay? And last time we had a couple more problems to do on basically finding the intervals of increase and decrease. So I wanted to kind of do these last 2 problems before we move on to the next section. So let me just put a little line here so we don't get confused on that last problem we did. And again, just to remind you guys, this is, you were supposed to find the intervals of increase and decrease over this guy. Now, to find intervals of increase and decrease, we need to figure out basically about the derivative. Because increasing is where the derivative is positive, decreasing was the derivative is negative. So, first thing we need to do here is take my derivative. This problem here is x plus 2 divided by x minus 1. It is clearly a quotient. So to take derivative, I got to use the quotient rule. Derivative of the top times the bottom minus the top times derivative of the bottom all over the bottom squared. Knowing these rules and knowing the words are going to help you out so much more on this test. Derivative of the top, what's derivative of x plus 2 is 1 Here the top times the bottom, x minus 1, minus the top, which is x plus 2, times derivative of the bottom, which is 1, all over the bottom, x minus 1 squared. All over the bottom squared. But with these guys, you do have to clean them up. So I'm going to distribute a 1. This gives me x minus 1. I'm going to distribute 1, and I got to distribute the negative. And when you distribute a negative through stuff inside of parentheses, it changes your signs. So this becomes minus x minus 2 over x minus 1 squared. Here, x minus x cancels, and minus 1 minus 2 is a minus 3 over x minus 1 squared. Now, so there's my derivative, negative 3 over x minus 1 squared. We got to find two things with these particular functions, because we're trying to figure out when they're going to be positive and when they're going to be negative. So we got to figure out, well, first, for what points of this particular function does the derivative not exist? Well, a derivative, a function, doesn't exist when the denominator is equal to 0. So I've got my D and E point, does not exist for the derivative, is when the x minus 1 squared, the denominator is equal to 0. If I can take the square root of that, I get x minus 1 equals 0, which means x equals 1. The other point you need to find is the 0 point. You find a 0 by taking the function and setting equals 0. But in this case, my derivative, which is negative 3 over x minus 1 squared, when you set it equal to 0, how do you solve that guy? Well, you got a fraction equal to 0. You do the same thing every time. You get rid of your denominator because you don't want fractions when you're solving equations. So I'm going to multiply both sides by x minus 1 squared. And look what happens. It completely cancels here, and you're left with a negative 3 equals 0 times x minus 1 squared is 0. I got negative 3 equals 0. First off, negative 3 doesn't equal 0. Next thing you should notice is all the variables went away. There are no variables. And since there are no variables, there's no solution. No solution meaning there is no 0 points on this guy. There's only 1 point on this guy, the point that doesn't exist. But again, to find intervals, you hear that word intervals? Intervals of increase and decrease. Anytime you hear the word intervals, you're going to draw a number line. So I'm going to draw my number line, and for intervals of increase and decrease, that is a first derivative number line. And I'm going to put my point of non-existent here of 1. I got to mark either the 0 points and the points that don't make the derivative not exist. Put those on there and put circles around them. So that's going to subdivide my number line into 2 spots. So I'm going to do test values. Pick a number less than 1. Use your brain. Good choice. So I'm going to plug in 0 into my derivative. Again, my derivative is negative 3 over x minus 1 squared. Plugging in 0 is negative 3 over 0 minus 1 squared. This is negative 1 squared is negative. Negative 1 squared is positive. So this is negative 3 divided by 1, which is negative 3. I don't care what the number is. What's the sign of it? It's negative, so everybody in this interval is going to be negative. Does that make sense? Did I lose you guys anywhere? Now, pick a number bigger than 1. 2. F prime of 2. Because when you plug in, you get negative 3 over 2 minus 1 squared. Negative 3 over 1 squared. 1 squared is 1. That gives you negative 3. It's still negative. Notice the signs don't change. It happens. Sometimes they change, sometimes they don't. This one doesn't change. So what does this tell you? In terms of my answer, they want to know what is intervals of increase and what's the intervals of decrease. That was the question in this particular problem. Where is this function increasing at? Where is it? For increasing, the derivative is positive. Where's the derivative positive at? Nowhere. So symbol for that is an empty set, 0 with a line through it, or does not exist, no solution, however you want to put in the blank there. No solution. And the symbol for that is 0 with a line through it, the empty set. Where is it decreasing at? You still have to skip over 1 because 1 doesn't exist, so pretty much everywhere else. That'll be negative infinity to negative 1 union, that's positive 1 now. Negative infinity to positive 1 union positive 1 to infinity. Does that make sense? That is my intervals of decrease. It's decreasing from negative infinity up to 1 and from 1 to infinity. Does that make sense? So this is my solution for this problem. In a similar light, take a look at this last one here, because you know it's going to be in our word problem format here. A store manager has determined the revenue of the sale of X units of a product is given by, well, Merry Christmas, they gave you the revenue equation here. R of X equals 32X minus 0.4X squared dollars, where, here it is, 0 is less or equal to X, which is less or equal to 80. What is the intervals of sales? On what interval is the sales of the revenue increasing, and on what interval is the sales decreasing? Okay, same idea. We want intervals of increase and decrease. But this is something special. They gave me an interval between 0 and 80. All I care about is between 0 and 80. I don't have to go from negative infinity to infinity. So remember that in terms of your answer. Other than that, I'm going to do the same thing. First thing I'm going to do is I'm going to get my marginal revenue equation. I'm going to take my derivative. What's the derivative of 32x? 32 minus, what's the derivative of 0.4x squared? Well, 2 times 0.4 is 0.8x. Does that make sense? There's my derivative, 32 minus 0.8x. I'm going to find where it's equal to 0. First off, you notice there's no fraction here, so I don't have to worry about points that don't exist, but I do need to find my 0 points. So to find the 0 points, and just to get you guys set for the next section stuff, 0 points, where the derivative is equal to 0, is also known as the critical points. Terminology, setting you guys up for the next section here. So we're going to find the critical points by setting the derivative equal to 0. I'm going to solve this guy. I'm going to add 0.8x to both sides. That gives me 32 equals 0.8x. And then I'm going to divide by 0.8 on both sides. And I get x is equal to, and grab my handy dandy calculator here. And here it is. 32 divided by 0.8 is 40. X equals 40. So to find my intervals of increase and decrease, I'm going to draw my number line. And I'm going to put 40 on my number line, because that's where my derivative is equal to 0. But I'm also going to put something else on my number line. The values of where the function is defined. And what is that? Between 0 and 80. And I'm just going to mark through less than 0 and greater than 80, because I don't care about those guys. So I'm going to put my 0 and 80 on this number line, because that's where my function is defined to be. Does that make sense? So something new has been added in this word problem. Just instead of negative infinity to infinity, they closed it in just between 0 and 80. So now, here we go. I'm going to do test values. Remember, this is a derivative number line, and r prime of x was equal to 32 minus 0.8x. So let's pick a test value. Pick a number between 0 and 40. There you go, good 1, fine. So this would be r prime of 1. This would be 32 minus 0.8 times 1. Well, 0.8 times 1 is 0.8. 32 minus 0.8 is going to be 31.2. You chose 1. All right? Don't care what the number is. What's the sign of it? It's positive, so everybody in that interval is positive. Now pick a number between 40 and 80. I'll choose 60 just to be different right in the middle there. Okay, r prime of 60. Honestly, it doesn't matter which point you choose. You can pick 41 if you want to. I'm going to go for nicer numbers here. So this is equal to 32 minus 0.8 times 60. So 32 minus 0.8 times 60 is negative 16. But don't care what the number is. What's the sign of it? Negative. So everybody in that interval is negative. Now to answer the question. The question is, on what intervals is this revenue increasing and what intervals is the revenue decreasing? It is increasing on what interval? And we always use open parentheses, from 0 to 40. Notice I didn't use negative infinity on this one. We only talking about between 0 and 80 here. So between 0 and 40 is where the revenue function is increasing. And where is my revenue decreasing? Between 40 and 80. Does that make sense? Did I lose you guys anywhere? Now, let me set up for the next section that I'm going to be talking about. This is also telling me something else. In terms of revenue, let's understand what's going on here. between 0 and 80, my revenue is increasing. It's going up. Between 0 and 40, my revenue is going up. Between 40 and 80, my revenue is going down. That's going to make 40 a very special point. Granted, it's a critical point, but better yet, if I go up and then come back down, what kind of point is it? If you go up, hit the point, and come back down, what kind of point is it? It's a maximum point. You hit the top. When you go down and hit the point and go back up, you have a minimum point. So this is called, what I'm talking about is called the first derivative test, because of these first derivative equal to 0, these points, these critical points, are where you find your maximums and minimums. Now, let's talk about that from a business perspective. The old adage in terms of business is if you're selling, let's talk about stock market. How do you make money in the stock market? What do? The old adage. You buy low and sell high. But you got to figure out where's your highs and your lows going to be at. Well, that's where your expertise comes in at, understanding what your market or whatever you're dealing with and stuff. But once you can identify these highs and lows, these maximums and minimums, that's knowledge and that's power, because you now know when to sell and when to buy. Does that make sense? Also, in this particular problem, 40, because you went up, hit 40 and come back down, 40 is actually a maximum. It's going to be called a local maximum. Okay? And this 40 is actually where I should be shooting for. That's when I maximize my revenue. I should be shooting to sell 40 items. Does that make sense? Now, I know a lot of people think, well, why don't you just sell as much as you can? But you remember, price varies, right? Your price varies. So your revenue based upon that price is going to vary. So if I sell too many, my price is going to be dropping because I've sold so much, competition and the like. So even though I sold a lot, I may not be making as much money as I could have been. My target in this problem to maximize my revenue is I should be shooting to sell 40 items, okay? And with that varying price and stuff, hitting that 40 mark, my price is going to be at the top. My number I'm selling is going to be at the top. It's going to, quote, maximize my revenue. And this idea is very important because think about it. At the end of the day, the ultimate goal is to maximize profit and minimize cost. So these maximum minimums are going to be very, very important in the rest of your college career. Does that make sense? Maximizing and minimizing. This is a very important concept. So that is what section 3.4 is all about. Critical points and what we call this first derivative test. Really using this number line. So, but to get you started on this thing, a couple of ideas here. A critical point. A critical point of a function f of x is two places. And so we're defining the word critical point. So this is a definition. A critical point of a function f of x is where the derivative is equal to 0 or where the derivative does not exist. This is how you find critical points. You take the derivative and you set it equal to 0 and solve, and you also have to identify where the derivative does not exist at. Now, this idea of the derivative doesn't exist from a function perspective, yeah, I got to worry about where I divide by 0 and things like that. But from a graphing perspective, you know, here's what's really going on. If I graph the actual function f of x, I'll give you kind of f of x here. Let's say the function looks like this. Comes in, does this, and does something like this. There's my graph. On this particular graph, I've got two very special critical points. My critical points are, I'm going to call this guy x1. He's going to be here. And the other one is going to be x2. It's going to be here. x1 is what we call a local maximum. And we use the word local because I mean, in a neighborhood around this guy is the biggest point around. So this is going to be what we call a local max. This point right here is what we call a local minimum, because it's the smallest point around. But we call it local because in just a little neighborhood around it, it's the biggest and smallest point around. But if you go to take the function down the road far enough, maybe you'll get bigger points, maybe you'll get smaller points. So just in a neighborhood around them, this is going to be your max and your min. That's what we're after. Now, in terms of the ideas, if you look at this point, this maximum point, maximums, or I could have flipped the graph upside down, minimum. If you look at it, the slope of the tangent line right here is what? It is a horizontal tangent line. So this is where the derivative is equal to 0 at, because it has a horizontal tangent line. That's what happens at max and mins. You have horizontal tangent lines. The derivative is equal to 0. But you also have some special points. You see this guy here? This is called a cusp, a quote-unquote sharp turn in terms of a graph. Sharp turns are where the derivative at this x2 does not exist. Okay? That's basically we're trying to find where the horizontal tangent lines are at and where the sharp turns are located at. This is where your max and mins are going to be at. Okay? This is the idea behind the critical point. Now, carrying it on, when we have something called the first derivative test. Now, the first derivative test is analyzing that number line of the derivative. So you had your critical points here at x1 and here at x2. I'm just going to put two of these guys on here. And let's say I did this. This was plus, 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 increasing, and then over here it was decreasing, and then it was increasing again. Okay? This is the first derivative. So between negative infinity up to x1, we're increasing. Between x1 and x2, we are decreasing. Beyond x2, we're back to increasing again. Does that make sense? This is called the first derivative test. It's analyzing your number line for the first derivative, your intervals of increase and decrease. So if you increase and you hit the point up here and then you decrease, what does that make x1? That means x1 is a what? It's at the top. It's going to be a maximum. What we're going to call this is a local maximum, because you go up and hit it and come back down again. You go down and hit x2, and then you go up again. What does that make x2? So if you go negative and then positive, what does that make x2? x2 is a minimum. x2 is we call it a local minimum. We'll talk about absolutes in the next section. Okay? This is that first derivative test. But what if I had this? Here's x1 and here is x2. You got negative, then you got positive, then you hit x2 again, and then you got more positives. For analyzing this particular number line for some weird function f of x here, this is f prime of x, what can you tell me? Well, between negative infinity to x1, I am decreasing. And from x1 to x2, I'm increasing. That means x1 is what kind of point? You go down and then you go back up. What does that make it? Minimum. This would be a local minimum. What about x2? You go up, you hit x2, and you go up some more. You know what that makes x2? Nothing. It's not a max or a min. Because to get a max, you've got to go up and come back down. To be a minimum, you've got to go down and come back up. To go up, hit the point and go up some more, it's not maximizing and it's not minimizing. Does that make sense? It's not going to be a max-min point. Does that make sense? This is the first derivative test. So, these are your ideas with your terminology. So let's go fill in our blanks in terms of our learn stuff from our Hawks and from the learn mode off the Hawks stuff there. So here we go. First question is this. Under the learn mode, the points where the function changes from increasing to decreasing or vice versa is called and I give you the big terminology for it, local extrema. Local extrema. That's when you put both max and mins together. Where you has a maximum or a minimum, the general terminology is your local extrema. Your extremes, the max and the mins, but local extrema is the terminology for that. Okay? Number two, if there exists some point A to B, some point in, if there exists some interval A, comma, B that contains C such that f of x is less than or equal to f of C for all x in between A and B, we say f of C is bigger than all the other points. What's that guy going to be called? A local maximum. And similarly, if there exists some interval A to B that contains a C where such that f of x is greater than or equal to f of C for all x in the interval between A and B, we say f of C, greater than or equal to f of C is on the bottom. That makes him a what? Local minimum. We say that the local extrema is equal to blank and occurs at the blank. All right. So the local extrema is equal to f of C and occurs at x equals C. Now let me explain. This is terminology. All right. So in this particular spot right here, they're going to ask you some word problems. When they ask you for the, quote, maximum value, max or min value, you hear the word value. That's the y coordinate, because you're going to have a max min point. You're going to have an x coordinate and you're going to have a y coordinate. The max min value is the y coordinate. It occurs at is the x coordinate. The max min value is the y coordinate. When you hear the word value, you want the y coordinate. It occurs at, that's going to ask you for the x coordinate of the point. So we're going to be finding max and min points, and then they're going to ask you a word problem, and you've got to answer the question by giving them the right coordinate. The value is the y coordinate. It occurs at is the x coordinate, and that's what they're referring to here. The local extremum, max min, is equal to, the value is going to be f of C, and it occurs at, that's going to be your x coordinate, x equals C. Okay. 5. If a function, f, is continuous on the interval between a and b, and c is in the interval between a and b, and f of c is either a local maximum or a local minimum, then f prime of c equals what, or f prime of c what? So how do you find a critical point? There's two ways to find a critical point. It's where the derivative is equal to what? 0, and where the derivative does not exist. So when I'm looking for extrema, I've got to first take my derivative, set equals 0, and solve. That's, I keep drumming that into your head now. To maximize or minimize, you take derivative, set equals 0, and solve. And where the derivative doesn't exist at. So the last thing I do is look at it and go, is there a point where the derivative doesn't exist at? But the first thing I'm going to do is take derivative, set it equals 0, and solve. So that's my phrase that you guys are going to be drummed into it. That's why calculus is so important. To maximize or minimize any function, you take derivative, set equals 0, and solve. And where the derivative doesn't exist at. Okay? The value c in the domain of f, where f prime of c is equal to 0, or f prime of c does not exist, is called the critical values of x. Critical values, critical points. So when I ask you for a critical point, those are the points where the derivative doesn't exist and where the derivative is equal to 0. Okay? And they're the x points. The critical values is x. The critical points, you get an x and a y. Okay? Local extrema only occur at these critical values. That's why they're so important. This is why I gotta find these guys. So if I'm looking for maxes and mins, I want these derivatives equal to 0 or derivative doesn't exist, because that's where it's gonna occur at. But a critical value does not guarantee a local extremum. Do you remember that example I did a few seconds ago where we had a derivative equal to 0 at some x2, but when I looked at my number line, I increased, I hit my point and increased some more. It's a critical point, but it's not an extremum. To be extremum, you've got to increase and then decrease, or decrease and then increase. You've got to change signs on your number line. That's what's going on. Okay. One more of these local extrema problems here. To determine the local extrema for a non-constant function f continuous on an interval, okay, here's basically your steps. 1A, find the critical values. X values in C in the interval between A and B such that f prime of C is equal to 0 or f prime of C is undefined. You got to first find your critical values. And then you're going to draw, and this is the Hawk's terminology for this, the analysis line. The analysis line is my number line for the derivative. Okay? That's what they call an analysis line. Okay? Because that analysis line is going to identify what kind of critical points you're going to have. When you go up and then go back down, you've got maxes. You go down and then go back up, you've got mins. So when I go from positive to negative, it's a maximum. When I go from negative to positive, it's going to be a minimum on your analysis line, my first derivative number line. Okay? And then that being said, here it is. Okay, check on the sign of f prime of x on each side of x equals c. If the sign changes, if it goes from positive to negative, then f of c is a local, you got it, maximal. And if I change from negative to positive, that's what I was just talking about, going down and going back up, I have a local minimum. Okay, if there is no sign change for f prime of x from the left side of x equals c to the right side of x, to right side, then f of c is not a local extremum. All right, so we're doing the same stuff. We're just doing more of it. So here we go. Take a look at this video example from your Hawks TV. Again, when you watch Hawks TV, they do a problem similar, but it's not the exact same problem here. Okay, you're supposed to, now look at the steps. Find the critical values for the function f of x is equal to negative 2x squared minus 36x minus 5. Then we're going to use the first derivative test to identify what kind of critical points we have now. Okay? So here we go. Critical values, and this is now terminology stuff. To find critical values, first thing I'm going to do is take my derivative, set it equal to 0 to solve, and look for where the derivative doesn't exist at. Well, what's the derivative of this guy? Derivative of negative 2x squared minus 36x minus 5 is minus 4x minus 36. There's my derivative. Negative 4x minus 36. To find a critical value, I'm going to take derivative, set it equals 0, and solve. Well, I'm going to add 36 to both sides, so negative 4x equals 36. I'm going to divide by negative 4. And 36 divided by negative 4 gives me x is equal to negative 9. The value is the x-coordinate. Critical value, also known as critical number, is the x-coordinate. The answer for this problem is x equals negative 9. Does that make sense? Now we want to figure out what kind of guy this is going to be. Okay? So I'm going to do a number line. So this is my f prime of x. I'm going to put my critical point negative 9 on here. Oh, by the way, look at this function. Negative 4x minus 36. Is there any point that the derivative does not exist at? No, it's just a linear term. I'm not dividing by anybody, so I don't have to worry about that. But I'm going to do a number line off this guy. So I'm going to pick a number less than negative 9. I'm going to plug it into my derivative. So f prime of negative 10. Let's say this will be negative 4 times negative 10 minus 36. Negative 4 times negative 10 is 40. Minus 36 is 4. I don't care what the number is, it's positive. Now pick a number bigger than negative 9. I choose 0, of course, because I have a brain. So plugging in 0 into this guy, I get negative 4 times 0 minus 36, which is equal to negative 36. It's negative. What kind of point is negative 9? By the first derivative test. Your analysis line here tells you. I'm going to go up, I'm going to hit negative 9, and I'm going to go down. It is going to be a maximum. You got it. So this makes it a, you said, local maximum. But now let's answer the question. We want a critical point. So to get, you've got x equals negative 9. How do I find a y coordinate? What do I have to do? To find a y coordinate, what do? You plug it into the original equation, f of negative 9. So I'm going to go all the way back to my original equation here. This would be negative 2 times negative 9 squared minus 36 times negative 9 minus 5. Time for the handy-dandy calculator here. Plugging this guy in, negative 2 times negative 9 squared minus 36 times negative 9 minus 5, and I get 157. So the critical value was x equals negative 9. You with me? If I say the critical point requires an x and a y coordinate. The point would be negative 9 comma 157. You got to take negative 9 and go back and plug him into the original equation. Okay? So, to answer the question, okay, we have a local, what was it? Maximum at the point negative 9, 157. The maximum value would be what? What would be the maximum value of this particular function? When you hear the word value, what are you going to give me? The y coordinate. What is that? 157. It occurs at, you give me the x coordinate. X equals negative 9. It occurs at negative 9. The value is 157. Does that make sense? And in terms of local means, the answer would be none. There are no local means. We only had one critical point, and he's a max point. Does that make sense? So we're going to play word problem games with this stuff, but it's real easy word problem games as long as you understand the words. When you ask for the value, give me the y coordinate. Occurs at the x coordinate, and this is how you find your critical points. Very important stuff in this scheme of business calculus. So let's do some more problems here. Find the critical values and use the first derivative test to identify any local extremum. Okay? So here we go. First thing I do to find max and mins, I'm going to take my derivative. Welcome to Calculus 101. Take derivative. So what's derivative of 2x to the 5 halves? We'll take derivative of that would be what? 5 halves times 2 would be 5x to the, subtract 1, that would be 3 halves. Minus, what's derivative of 320x? 320, and derivative of minus 12 is 0. So the derivative of 2x to the 5 halves minus 320x minus 12 is 5x to the 3 halves minus 20. Okay? Now, I'm going to set it equal to 0, and I'm going to solve. I'm going to add 320 to both sides, so I get 5x to the 3 halves is equal to 320. I'm going to divide by 5 on both sides, so I get x to the 3 halves power is equal to, grab that calculator again, 320 divided by 5. I get 64. Now I got a question for you. What do you got to do on the algebra end of this thing to solve for x? I got x to the 3 halves power equals 64. What kills off that 3 halves power? What I do to one side, I do the other. What kills off a 3/2 power is raising it to the 2/3 power, the reciprocal. What I do to one side, I do to the other. So x, because this will cancel, because power to a power you multiply, x would be equal to 64 to the 2/3 power. So I'm going to put that on my calculator. 64 raised to the 2/3 power is 16. And understanding your radicals, remember 2/3 power of 3 is the cube root, and you square it. The cube root of 64 is 4, squared is 16. So you can do it in your head if you want to, but use your calculator, it's fine. So, and if I look at this guy, there are no points where this derivative does not exist at, so there is my value right there. Okay, now, I'm going to put it on a number line. Here is 16. This is a derivative number line. My derivative, just to remind you, is 5x to the 3/2 minus 320. I'm going to pick some test values. My first test value, I'm going to plug in less than 16. I choose 0. And it'll be 5 times 0 to the 3/2 power minus 320. 0 to any power of 0 times 5 is 0 minus 320 is negative 320. I don't care what the number is. It's negative. So everybody in that interval is negative. Pick a number bigger than 16. I choose 17. So f prime of 17 would be 5 times 17 to the 3/2 power minus 320. Grabbing the old handy dandy calculator on that one. 5 times 17 to the 3/2 power. Whoops, the wrong button there. 3/2 power minus 320 is 30.463 something or other. I don't care what the number is. What's the sign of it? Positive. Everybody in this interval is positive. So now, from my analysis of the number line here, what do we got? We're going down, we're hitting our critical point and going back up. What does that mean we got? We got a minimum, local minimum. So we have a local minimum at, and my point would be x is 16. And how do I get that y coordinate? What do I got to do to get the y coordinate? Plug it back into the original equation. So f of 16 would be equal to 2 times 16 to the 5/2 minus 320 times 16 minus 12. And when I put that on the calculator, just to show you that I can, 2 times 16 to the 5/2 power over arrow minus 320 times 16 minus 12. I get negative 3,084. This is your local minimum point. 16 comma negative 3,084. Does that make sense? Take a look at the next dot. One more. Here we go. Take derivative of this guy. What rule would you use to take derivative of this thing? Negative 6 times 3x squared minus 12 squared plus 9. Chain rule. 2 times a negative 6 is a negative 12. 3x squared minus 12 raised to the first power times the derivative of the inside. Derivative of 3x squared is 6x, and plus derivative of 9 is plus 0 there. Okay? So this is equal to, and notice, I'm not going to clean it up because it's already factored. Set it equal to 0 and solve. When I set it equal to 0, you're going to set each factor equal to 0 and solve. So I get 3x squared minus 12 equals 0 and 6x equals 0. Solving for this guy, I'm going to add 12, so 3x squared equals 12. I'm going to divide by 3 on both sides. And I get x squared is equal to 12 divided by 3 is 4. What kills off a square? And when you take a square root, what do you got to do? Very good. Square root plus or minus. You're going to get x is equal to plus or minus 2. There are two answers there. And when I divide by 6, I get x equals 0. And so on my number line, I'm going to get negative 2, 0, and positive 2. And then I'm going to go do my test values. Does that make sense? Just wanted to show you the algebra, and don't forget your plus or minus. We'll finish up the rest of these problems next time, and then go on to the absolute max stuff. And I will have for you guys next time your next homework set. I'll pass out one to you guys, okay? And I also put it on your Canvas site, so pay attention to that.
Do you have my test? I wasn't here last time.
Sonda says.